Thank you, Mr. Chairman, and good afternoon, ladies and gentlemen. I'm going to talk about pressure-dependent plasticity models for incompressible granular materials. It is a phenomenological approach. And in the literature, several models of this kind are available, but it seems to me that there is no commonly accepted model. And selection criterion we propose in this paper is based on mathematical features of solution behavior based on different models. The point here is that most of such models are obtained as generalizations of classical rigid perfectly plastic material. However, not all solutions based on pressure-dependent plasticity models reduce to the classical solutions under certain value of parameters under which the equations reduce to rigid perfectly plastic equations. And this is a qualitative difference in solution behavior can serve as a selection criterion for this or that model. And this is the main goal of my talk today. And I will consider three pressure-dependent models: this coaxial model, double shrink model, and double slip and rotation model. And I'm going to compare solutions based on these models for one specific problem with the solution based on classical rigid perfectly plastic material model. So this is pressure-independent model. But these three models are generalizations of this one. And the system of equations can be divided in two groups. So the first group is shown here on this slide, and these equations are the same for all four models. It consists of, it's a reduced system for plane strain axisymmetric deformation. So it consists of two equilibrium equations, yield condition, and incompressibility equation. So the classical pressure-independent model is obtained if phi equal to 0. And so these equations are the same for all models. So the only difference in models occurs in the last equation, which relates the state of stress and strain rate. So in the case of coaxial model, the equation is given here. So psi is the orientation of major principal stress relative to r direction. So in the case of double shrink model, we have this equation, and in the case of double slip and rotation model, we have this equation. So if phi equal to 0, which is again pressure-independent plasticity, then all equations coincide. It is the same. So if phi is 0, this is cancelled, and so it is the same equation. And the boundary value problem considered is simultaneous shearing and expansion or contraction of a cylinder. This looks like classical coed flow, but it is not. It is, in addition to shearing, there is expansion or compression of the cylinder, because we want to create this more complicated state of stress and strain rate in the cylinder. So it's plane strain and axisymmetric. Therefore, the system of equations shown before is applicable to this problem. Of course, it's not visible for practical realization, but it is an ideal problem to understand the mathematical features of solutions. And the boundary conditions are formulated here. It is the rate of expansion or contraction of this radius is given, and then we assume that this surface is fixed against rotation, and also in the case of sticking, the velocity is prescribed here, and these conditions actually, it is not necessary to understand the general features of the solution, but for completeness of the boundary value problem, we have to impose the condition on the radial stress somewhere, for example, at this radius. Without loss of generality, we can assume that the psi is between pi over 2 and 0. It just determines the direction of rotation, so it's not important. So this system of boundary conditions is valid in the case of sticking, but we may have sliding here, and to describe this sliding, we assume the maximum friction law, and its physical meaning is that the friction surface coincides with an envelope of characteristics, and sorry, it's mathematical meaning, but physical meaning is that solution cannot be extended beyond this surface because it's envelope. We cannot extend solution beyond this line, and that's why the name is maximum friction law. We cannot apply larger friction. It's just based on the system of equation. And in the case of double sharing and double slip and rotation model, the characteristics for velocity and stress coincide, and therefore the friction law can be formulated in this way. So this is the orientation of characteristic direction, so it should coincide with friction surface. However, in the case of coaxial model, characteristics for the velocity and stress do not coincide, and therefore there are two options. One option is that stress characteristic coincide with friction surface, and the other option is that velocity characteristic coincide with friction surface. And on the next slides, I will explain the difference between these conditions, and actually this difference has a great effect on the general behavior of solution. So this is just for coaxial model. And if psi is larger than pi over 4, then we have the following structure of characteristics in the vicinity of friction surface. So this is the friction surface, and this major principal stress direction. And there are two characteristics here. One is velocity characteristic, and the other one is stress characteristic. And if this condition is satisfied, then you can see that the tangent to the friction surface is between major principal stress direction and velocity characteristics. Therefore, once as we move to the friction surface, so this structure is just rotate because these angles are fixed, so they're constants. So this structure can just rotate. And you can see from this diagram that the only possibility in this case is that this characteristic direction coincides with tangent to the friction surface. This one cannot coincide because this comes first. So it is in the case of psi larger than pi over 4. And the third case, if psi is less than this value, and in this case, the structure of characteristic directions in the vicinity of friction surface is shown here, and it is now opposite. It is now the only possibility is that stress characteristic direction coincides with tangent to the friction surface, because it comes first. It can rotate and coincide with this line, but this line cannot be tangent to the surface if this condition is satisfied. And finally, the third case, if psi is between these two values, and then the tangent to the friction surface is between two characteristic directions, and both cases are possible. So this is the difference in the structure of characteristic directions in the vicinity of friction surface. And then analytical solution to this problem has been found, and this part of the solution for stresses, is independent of the model. All models, we have the same solution because problem is statically determined. So this means we use just equilibrium equations and yield condition, and we can find the state of stress. And gamma is a constant of integration. But the solution for velocities, of course, depends on the model now. And the radial velocity is given by this equation independently of the model. So the only difference is velocity in theta direction. So in the case of coaxial model, we have this expression for this velocity. And in the case of, well, we'll analyze these equations later. So this is for double shrink model, and this one is for double slip and rotation model. So there are two arbitrary constants, gamma and Ca, for all three solutions. And we have to find these constants based on using the boundary conditions. So this is a coaxial model. This is the structure of the final equation we have to solve. And first, we can mention that the integral is singular if psi equal to pi over 4, because it becomes 0. And therefore, the interval, the total interval from 0 to pi over 2 may be decomposed into three subintervals between 0 and this value, and then between this value and pi over 4, and finally between pi over 4 and pi over 2. And then the solution behavior depends on which interval occurs in the actual solution. So also it depends on the mode of deformation. It is compression or expansion of the cylinder. So in the case of contractions, there are two possibilities, and one is the subinterval from 0 to this value, and in this case, this relation between psi b and psi a is satisfied, and sticking occurs. So we don't have no sliding. Sticking occurs in this case. And if Ca less than this value and sliding occurs at psi b equal to this number. And this subinterval never occurs if you have contraction. And if you have expansion, then in this subinterval, there is this relation between psi a and psi b, and only sticking occurs here. There can be no sliding, and the velocity is unbounded at r equal to a, if psi equal to pi over 4. So this is the structure of solution for coaxial model. In the case of the double shrink model, the sliding occurs if this condition is satisfied, and this the structure of this solution is qualitatively the same as in the case of rigid perfectly plastic material, classical plasticity. However, there is another option here. If sticking occurs, that we have this equation, and the equation can be regarded as the linear first-order differential equation for psi a. However, the problem here is there is no initial value for psi a to solve this equation. Therefore, actually, in this regime, there are infinitely many solutions, and this is a great difference from the classical case. And finally, in the case of double slip and rotation model, we have this kind of solution, and in this case, we have the unique solution at sticking if this condition is satisfied, and unique solution at sliding if this condition is satisfied. So the conclusion is that the only model of considered models qualitatively coincide with classical model. It's the only double slip and rotation model retain all qualitative features of the solution based on the classical rigid perfectly plastic solutions. Other models leads to different, qualitatively different results. Thank you for your attention.
Questions?
Your velocity may be dimensionless using the rate of dilatation of your
right.
cylinder. So what happens when you have not this dilatation? Would you just have a simple quet?
It is, well, in the case of rigid perfectly plastic model, the solution reduced just to single discontinuity line. So it's not good for comparison.